Hey everyone, and welcome. It's funny how some of the biggest ideas in mathematics are hiding right in front of us, in everyday objects. Today, we're going to pull back the curtain on a geometric rule you've used 1,000 times without even thinking about it, every time you open a door or swing a gate. And then, we'll see how that simple idea can solve some really complex, real-world problems. It's going to be fun.
So, let's start right there, with a simple swinging gate. Imagine you're opening one. Now the length of the gate itself, that's not changing. And the distance from the hinge over to the fence post it latches onto, that's fixed too. But as you swing that gate open, there's one key distance that absolutely is changing. And it's this. The wider you open the gate, the bigger the angle gets, the farther the end of the gate is from that fence post. It just makes sense, right? A tiny crack means they're close, swing it wide open, and they're far apart. This super intuitive relationship is the key to, well, pretty much everything we're about to get into.
Okay, so this whole gate idea isn't just a neat observation. It actually has a formal name in geometry, and that name gives us the power to use it as a serious problem-solving tool. So let's go ahead and put an official name to this thing we already get.
It's called the hinge theorem, and here's the official definition. It says that if you've got two triangles, and you know for a fact that two sides of one triangle are the exact same length as two sides of the other, just like our gate and the fixed fence distance, then whichever triangle has the bigger angle in between those two sides is going to have a longer third side. It's literally the gate principle, just dressed up in math language.
And check this out. This visual shows it perfectly. See those little tick marks? They tell us that both triangles have two sides that match. But just look at the angles between them. One is a wide 88 degrees, and the other is a much smaller 35 degrees. Because 88 is bigger than 35, the hinge theorem guarantees, no question about it, that the side across from it, WX, has to be longer than the other side, ST.
Okay, but what if we flip the script? What if we know the side lengths, but we don't know the angles? Can we work our way backward? Oh, you bet we can. This is called the converse. It's the same exact relationship. We're just looking at it from the opposite direction.
So, the converse of the hinge theorem basically just reverses the logic. It says, okay, you've got those two triangles again, with the two pairs of matching sides, but this time, if you know that one triangle has a longer third side, then that triangle must have the bigger angle squished between its matching sides.
And boom, here's a perfect picture of the converse at work. Again, we've got our two pairs of matching sides. But this time, they give us the lengths of those third sides. One is 12 and one is 9. Well, since 12 is obviously bigger than 9, the converse tells us, with total certainty, that the angle across from that side of 12, which is angle C, has got to be bigger than the angle across from the side of 9, angle F. See? We worked backwards from the side to the angle.
All right, I think we've got it. We have the hinge theorem and its trusty sidekick, the converse. Now let's put these new tools to work and have a little fun solving some geometric puzzles.
Let's kick things off with this one. Take a good look at the diagram. We have this one big triangle that's been split into two smaller ones. Now, we're told that side JK is the same length as side LK. And you can see they both share that middle side KM. So, with that in mind, how does the third side, JM, stack up against LM?
And the answer comes right from the hinge theorem. We have our two pairs of matching sides. So what's next? We look at the angles between them. One is 64 degrees, the other is 61. Since 64 is bigger than 61, the side opposite that bigger angle, that's JM, has to be longer than the side opposite the smaller angle, LM. And that's all there is to it.
Okay, ready for another one? This time, we're going to need the converse. In this picture, we know the top sides match, and the two triangles share that diagonal side PS. We're told that PT is 24 inches long and SR is 23 inches long. So the question is, how do their opposite angles, PST and SPR, compare? Well, since side PT is 24 inches, and that's longer than side SR at 23 inches, the converse of the hinge theorem tells us exactly what to do. The angle opposite the longer side has to be the larger angle. So the measure of angle PST is definitely greater than the measure of angle SPR. Solving puzzles is great practice, but this is where it gets really interesting. Let's see how this theorem we've been talking about can actually help us figure out the winner of a race. This is the moment where we see why these abstract ideas really do matter. Okay, so here's the scenario. You've got two groups of bikers. They both start at the exact same spot.
They both ride for 2 miles. Then they both make a turn, and then they both ride for another 1.2 miles. Everything is identical except for one thing: the turn they make. Group A makes a 45-degree turn, while Group B makes a 30-degree turn. So, which group ends up farther from where they started?
Now, whenever you get a word problem like this, it's a really good idea to have a game plan. So we're going to follow these 4 simple steps. First, make sure we understand what's being asked. Then, we'll make a plan. After that, we solve it. And finally, we'll take a quick look back to make sure our answer actually makes sense.
So for our plan, the absolute best way to tackle this is to just draw a picture. And the second we start sketching it out, something should look really familiar. The path for each group of bikers forms a triangle. And not just any triangle, both triangles have a 2-mile side and a 1.2-mile side. Ding, 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 this is a textbook setup for the hinge theorem.
Okay, time to solve this. Now, we need the angle inside the triangle, the angle at the point where they actually turned. A straight path is 180 degrees, right? So, to find the internal angle, we just subtract their turn from 180. For Group A, that's 180 minus 45, which gives us an angle of 135 degrees. For Group B, it's 180 minus 30, which is 150 degrees.
And just like that, we have our answer. We've got our 2 triangles with 2 matching sides. We now know Group B's internal angle is 150 degrees, and that's bigger than Group A's 135-degree angle. So the hinge theorem tells us that Group B's third side, which represents their distance from camp, is longer. Group B is farther away.
So, we've seen the theorem, we've seen the converse, and we've seen it solve a real-world problem. To really make sure this concept sticks, I've got one last little challenge for you to chew on. A little what-if scenario.
What if we add a third group, Group C? They do the same thing, 2 miles, then 1.2 miles, but their turn is 40 degrees. How would their final distance from camp compare to Group A and Group B? Think about the angle you'd have to figure out for them and where it would slot in with the other 2. It really just goes to show how powerful and useful one simple geometric idea, like a swinging gate, can truly be.